This video will be about the Knight's Tour problem. I'll be discussing what the problem is, as well as some of the solutions present, and how to implement them in code. So, what is the Knight's Tour problem? To explain this problem, we can look at a chessboard. This chessboard, there's a knight. A knight has a peculiar way to move compared to the other pieces. To explain more about the Knight's Tour problem, we can look at a chessboard. This chessboard, there's a knight right here. A knight moves in a strange way compared to the other pieces. Its only two rules are that you can move two squares on one side, on one direction, and one square on the opposite direction. That means vertically and horizontally. So for instance, as you can see with the arrows, there are 8 possible squares that the knight can move to. Using this knowledge, the problem asks, is there a path the knight can take to visit every single square in a chessboard using that movement? There is one rule to this problem, and it's that you're not allowed to go back. So if you have been in this square, that means you can't just return. Using this rule, is it possible to cover all squares? So, thankfully, Wikipedia has a cool page explaining basically this problem. On the right side, you can find a cool video where the knight jumps through all the squares, and basically it shows that there's a solution for a 5x5 board. One of the biggest problems currently in computer science is that the solution is non-deterministic. That means, in few words, that given a state, so given an initial position, we don't know if there's a solution until we try. So what are some solutions to this problem? There's 3, at least, in the Wikipedia page. First one is backtracking. In other words, basically means a brute force solution where we try every single possibility in the board. And if we don't manage to get a solution on our first try, we just backtrack until we go to a position that has a solution, basically. The second solution is a Warnsdorff algorithm, which we are gonna talk more about later in the slides. And the most impressive, personally, the neural network solution. In this solution, every knight's move represents a neuron. Then, after training our neural network, the model will eventually find a solution. However, that's not always the case. If the values of those neurons do not converge to a specific value, then that model will not find the optimal solution. Okay, so now let's talk more about the Warnsdorff algorithm. Basically, it means move the knight to the square with the least amount of possible moves after you make that move. In this picture, we can see a knight on a chessboard with, in this case, 6 possible squares that it can move to. However, how do we make that decision? This algorithm tells us to go with a 2 because it's the smallest number among all the 6. How do we calculate that number? We basically pretend that this knight is in this place. Then we calculate again how many possible squares can the knight move to. In this case, there's only 2, this place and this one. Why not this one? Because going back to the rules, we cannot revisit a square, so there are only two. This algorithm also brings some problems. For instance, the problem with ties. What would happen if our least amount of possible moves occur in different squares? For instance, let's just ignore these three numbers and go with the 7. How would we decide where to go to? There are three main solutions. First one is check the number of possible moves at the next level, which basically means doing the same thing. After I move here, I would check the number of possible moves that I can make, and then go with the one with the least. Another solution is move orderings. I'm going to put a link in the description to a research paper which talks more about this kind of solution. The last solution is just to pick randomly. However, if you visit the research paper, there are some evidence that if you pick randomly, as the chessboard grows bigger and bigger, the chances of getting the correct path decrease. So it's better to go with the other two solutions. Okay, so now it's the time to implement the solution. For this solution, I'm going to use backtracking because I think it's one of the easiest to implement for now. We are going to visit the other solution later on, but right now I'm using Rust. This is how a normal file looks like. So if I go like this, when you do a cargo new project, this is how it should look like. So let's start. So first thing, we can just run this program to see if everything works fine. So cargo run. Nice, we get that. So let's start. First thing is we're gonna specify the size of our board. In this case, I'm gonna do it 5 by 5, just to make sure that we can understand the problem in a small scale, so we can later on understand it on bigger scales. So we also need to declare the moves that we want to make with a knight, the number of moves that a knight can move to the squares, right? So it's going to be an array of tuples, and of course there's 8 of them. So let's start. So to 1, that means you can move 2 to the right and then 1 up. I'm sorry, 1 down. The second one is 1, 2, which is 1 to the right, 2 down, and so on. You get the idea. So I'm just gonna keep going. There's one more. Let me take this out first. 2 and -1. So if I did it correctly, there should be 8 of them right here. I need a. Oh, sorry. There you go. So the 8 moves. Now I'm just gonna make a board right now. So what we're gonna do is declare a vector. Let solution, in this case we can call it board. It doesn't matter, solution. We're gonna leave it as solution. It's gonna be a vector of I32. A vector of a vector because it's a 2D vector. And we're gonna say for now that we want a vec of a vec, and the values that we want inside for now are -1, and we want 8 of them. We also want 8 vectors inside of that. Well, not really. I'm sorry. We need n of them. Now, something really funny about Rust is they're really picky with the types. So in this case, it says Rust was expecting a usize instead of I32. So to fix that problem, we can just cast the type of the variable. So as usize, and we can do the same thing with this one. And there you go. Now, we want some sort of way to display the board. So let's just make a function called display. Doesn't really matter what you call it. So it's going to be a board. We're going to take a board. It's going to be a vector. We want the reference. That's why I'm using the ampersand of a vector of I32. And it's not going to return anything. So we can just leave it like that. So for row in our board, in our vector, and for column in our row, we're just gonna print the column. That should be good. I forget it's a macro. Should work fine. And then display, and then we can just pass our solution as our vector as a reference. That should work. To make it better, I'm gonna add a print line statement here, and we can run this. Hopefully it works. -1, -1, -1, right? Something else I want to do is just to add some spacing between those, just to make it look better. So we have our board for now. We need our main function, which is the one that's gonna solve the entire thing. So first of all, let me copy and paste, delete and paste whatever we had there. Here we're just gonna call solve, right? So we have our board moves and all of that. We are gonna say that our first position is gonna be 0, 0. So the top leftmost square in a chessboard. Now again, Rust is really picky with the types. So here we're actually changing one of the values in the memory. So we need to specify that we want a mutable variable rather than just a normal variable. In Rust, all the variables are immutable by default. So for now, that's what we have. Shouldn't have deleted that, but we're good for now. So cargo run 0. We can just keep moving. So the function that's gonna do the hard work is gonna be called solved board. We're gonna leave it blank for now. So I'm just gonna do a quick explanation of what we want to do, right? So we start here, and like I said in the slides, basically the algorithm is to try every single possibility for now. So we're at this point we can move here or here, right? So we want to try those two things first, and then after we do that, using recursion, we're going to call the function again and again and again. So if we go here and then here, then the function would choose any of the possibilities, right? And if there's no solution, you're going to backtrack to the point where you can make another choice rather than that one that you already know it's not going to work. So for that, this function is going to take x. Sorry, I'm used to C and C++. X, a y at 32. We are also, just for visual purposes, we're going to take the number of steps, the step that we are currently on. Also the board, right? So the solution, and similar to the other function. It's going to be a reference of a vec of i32. And then we can move on, right? So the first thing we're going to check is if the step that we are currently on equals n by n. In other words, we are trying to check if we are at the end, if there are no more turns that we can go to. So if that's true, we're going to return true. I also need to specify the return type. So it's going to be a Boolean. And in case that nothing happens, I'm just going to return false for now. So now we want to iterate over all the possible moves that the knight can do. So for that, we can use a for loop that Rust provides. So 0 through 8, right? Because there are 8 possibilities. So we're going to declare a variable with the possible next x, as well as another one with the possible y that we can go to. So now we just take moves of next, and because it's a tuple, we want the first one for x, right? So this right here. And we do the same thing with y, but instead of 0, we're going to take the second one. Now we want to move to that position, right? However, there's a problem. For example, if we are at the top left square, there's no way we could move up 2 up and 1 right. So we need to check for that. So actually we need another function to just check if we are, if the square we are moving to is something allowed. So save, and we're gonna take int x. Again, I get confused. i32, y i32, and our board, and we already have that. We're gonna return a Boolean in this case. So basically, we're gonna check if our number is greater than 0, because vectors start at 0 in Rust. We are also gonna check the same thing for y. We are also checking if it's less than n, and for y2, because we don't want to go outside this range, outside this number, or this, horizontally or vertically. Last thing we're going to check is if our board at that exact location is a -1. So Rust, again, it's telling us to make the x and y as usize, because that's what it accepts to index a vector. So that should work. We can call that function saying if safe, and we're gonna tell it next x and next y, and also our board. If we can move to that that right there, we are gonna say our solution at that point. So next x, and just to avoid the problem as before, we are gonna just do it right now. We're gonna cast that i32 to a usize. Same thing for the next y, as usize, and we're gonna just say, okay, it's a valid square. So we're gonna just say this is the number of the step, right? Now it says cannot borrow solution as mutable. So now we need to specify mute in this right here to make changes to the variable. Now we're gonna call the function again, just to go further, right? So X is going to be next X, then next Y, the step plus 1 because we already we're moving to the next one. Then solution return true. So if we get at the end here, then that means it's a good solution. However, if none of this works, then it's going to be a false. And in that case, we're just going to say solution of next X. Actually, I'm just going to copy and paste this. We're going to say it's -1, so we're just backtracking. So now we're going to say if solve board, then we're going to pass. So it takes X, we're gonna start at 0 and then step 0 and solution, which is our board right now. Now we want to mute. We can just do that. Can we? Yes. If it returns true, that means it successfully found a path. So display, which is the function we did before, solution, and we want a reference to that. So yeah, to say I need a mutable reference of solution. Else, we're gonna say we're gonna print to the screen that there is no solution, and that's it. So in a 5x5 chessboard, is there a solution if we start at 0, 0? Let's just run it. As every tutorial, there's gotta be some mistake, some bug that you need to fix. If not, people are gonna suspect that you're not really teaching, right? So my problem was I forgot to add the previous X to the move that we're doing next. That problem was this line right here. It was passing a 0 for some reason, and it's a 1. The problem is, if I pass a 0, this if statement is never going to be true, so there's no solution ever. So if I go back to the 5x5, we find a solution. We can also change it to an 8x8 just to see if things hold true. And boom, it takes longer because there is more computing to do. However, we still find a solution. I would suggest you to try different numbers for the size of the board and also the initial position just to see if there's any changes. Thank you for watching this video where I explain what the Knight's Tour is and the backtracking solution. I'm planning to do another video explaining the Warnsdorff solution, but that will be later on. I'm also planning on doing a Git repo where I post my Rust solutions as well as a C++ equivalent. Once again, thank you for watching. If you have any questions, please let me know in the comments, and also visit my social media.